once again, first three-phase supply is given to the stator side. So rotating magnetic field is produces. So what is rotating magnetic field? That I will discuss in the next class. So please remember what is rotating magnetic field. So three-phase supply is given to the stator. Rotating magnetic field is produces. So stationary rotor is placed in between the rotating magnetic field, so that Faraday's law of electromagnetic induction, EMF is induced in the rotor current. So rotor side. So that EMF is what going to have do that is it is make current. That means as the rotor bar is short circuited, it is current flows through them. So it becomes the rotor is carrying the current and it is placed in the magnetic field. So motor starts to rotate. So this is how the induction motor is running. That means there is no need of starter. There is no need of starter for induction motor. Straight away, if I given three-phase supply, it is make the system to rotate, make the motor to rotate. Okay. So the highlights of three-phase induction machine is a self-starting and less armature reaction and brush sparking because of the absence of commutators and brushes that may cause sparks, robust in construction, economical, easier to maintain. Okay. So these are all about working principle of induction machine. Here I'm going to show you the video of how it's working. So please listen carefully, please watch it carefully and make understandable. Okay.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating, but At what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So there won't be any induced EMF and current. This means zero force on rotor bars. So the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So induced current and force will rise again, and the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction.
So this is what actually in that video actually you've gone through about how the three-phase induction machine is working. Okay, first thing, rotating magnetic field is produces. I recall again, when a three-phase supply is given to the stator's winding, rotating magnetic field is produces. And second case, that rotating magnetic field, when you placed stationary bar, conductor bars is placed in the rotating magnetic field as per Faraday's law of induction, and induced the EMF is produces. That induced EMF is making induced current or inducing current in the rotor bar side. So as per Lenz's law, when a current carrying conductor is placed in between the magnetic field, that means a force, a deflection force is produces. That is what we can call as torque. Okay, so this is what happening in a induction machines. So hope another important thing is it should not reach the synchronous speed. Why rotor speed should not reach the synchronous speed? The only thing is if both are equal, there is no deflection force is going to happen. So because it is producing constant magnetic field, so it cannot able to produce that means it cannot able to produce that deflection force or torque. So motor is going to stop. So this is not going to happen. So the rotor speed should always run less than a synchronous speed. So hope you understand about the basic principle of induction machine. So here two things, important things are used. One is Faraday's law of electromagnetic induction. Then second thing is Lenz's law. And third thing is rotor speed should not reach the synchronous speed. So these are the three important conditions. The next thing is slip. That means synchronous speed. Difference between synchronous speed and rotor speed is called as slip. So this is what we saw in this video lectures. So thank you one and all. The next class we can discuss about rotating magnetic field. Thank you.